The development of the principles of statics. Section 1. The principle of the lever. 1. The earliest investigations concerning mechanics of which we have any account, the investigations of the ancient Greeks related to statics or to the doctrine of equilibrium. Likewise, when after the taking of Constantinople by the Turks in 1453, a fresh impulse was imparted to the thought of the Occident by the ancient writings that the fugitive Greeks brought with them, it was investigations in statics, principally evoked by the works of Archimedes, that occupied the foremost investigators of the period. See page 510. 2. Archimedes of Syracuse, 287 to 212 BC, left behind him a number of writings, of which several have come down to us in complete form. We will first employ ourselves a moment with his treatise De Equiponderantibus, which contains propositions respecting the lever and the center of gravity. In this treatise, Archimedes starts from the following assumptions, which he regards as self-evident. A. Magnitudes of equal weight acting at equal distances from their point of support are in equilibrium. B. Magnitudes of equal weight acting at unequal distances from their point of support are not in equilibrium, but the one acting at the greater distance sinks. From these assumptions, he deduces the following proposition. C. Commensurable magnitudes are in equilibrium when they are inversely proportional to their distances from the point of support. It would seem as if analysis could hardly go behind these assumptions. This is, however, when we carefully look into the matter, not the case. Imagine, figure 2, a bar, the weight of which is neglected. The bar rests on a fulcrum. At equal distances from the fulcrum, we append two equal weights. That the two weights, thus circumstanced, are in equilibrium is the assumption from which Archimedes starts. We might suppose that this was self-evident entirely apart from any experience, agreeably to the so-called principle of sufficient reason, that in view of the symmetry of the entire arrangement, there is no reason why rotation should occur in the one direction rather than in the other. But we forget, in this, that a great multitude of negative and positive experiences is implicitly contained in our assumption. The negative, for instance, that dissimilar colors of the lever arms, the position of the spectator, an occurrence in the vicinity, and the like, exercise no influence. The positive, on the other hand, as it appears in the second assumption, that not only the weights but also their distances from the supporting point are decisive factors in the disturbance of equilibrium, that they also are circumstances determinative of motion. By the aid of these experiences, we do indeed perceive that rest, that is, no motion, is the only motion which can be uniquely determined or defined by the determinative conditions of the case. Now we are entitled to regard our knowledge of the decisive conditions of any phenomenon as sufficient only in the event that such conditions determine the phenomenon precisely and uniquely. Assuming the fact of experience referred to, that the weights and their distances alone are decisive, the first proposition of Archimedes really possesses a high degree of evidence and is eminently qualified to be made the foundation of further investigations. If the spectator place himself in the plane of symmetry of the arrangement in question, the first proposition manifests itself, moreover, as a highly imperative instinctive perception, a result determined by the symmetry of our own body. The pursuit of propositions of this character is, furthermore, an excellent means of accustoming ourselves in thought to the precision that nature reveals in her processes. We will now reproduce in general outlines the train of thought by which Archimedes endeavors to reduce the general proposition of the lever to the particular and apparently self-evident case. The two equal weights, marked 1, suspended at A and B in figure 3, are, if the bar AB be free to rotate about its middle point C, in equilibrium. If the whole be suspended by a cord at C, the cord, leaving out of account the weight of the bar, will have to support the weight marked 2. The equal weights at the extremities of the bar supply accordingly the place of the double weight at the center. On a lever, figure 4, the arms of which are in the proportion of 1 to 2, weights are suspended in the proportion of 2 to 1. The weight marked 2 we imagine replaced by two weights marked 1, attached on either side at a distance 1 from the point of suspension. Now again we have complete symmetry about the point of suspension and consequently equilibrium. On the lever arms marked 3 and 4 in figure 5 are suspended the weights marked 4 and 3. The lever arm 3 is prolonged the distance 4, the arm 4 is prolonged the distance 3, and the weights 4 and 3 are replaced respectively by 4 and 3 pairs of symmetrically attached weights of 1/2 in the manner indicated in the figure. Now again we have perfect symmetry. The preceding reasoning, which we have here developed with specific figures, is easily generalized. 4. It will be of interest to look at the manner in which Archimedes' mode of view, after the precedent of Stevinus, was modified by Galileo. Galileo imagines, in figure 6, a heavy horizontal prism, homogeneous in material composition, suspended by its extremities from a homogeneous bar of the same length. The bar is provided at its middle point with a suspensory attachment. In this case, equilibrium will obtain. This we perceive at once. But in this case is contained every other case, which Galileo shows in the following manner. Let us suppose the whole length of the bar or the prism to be 2 times m plus n. Cut the prism in two, in such a manner that one portion shall have the length 2m and the other the length 2n. We can effect this without disturbing the equilibrium by previously fastening to the bar by threads, close to the point of proposed section, the inside extremities of the two portions. We may then remove all the threads if the two portions of the prism be antecedently attached to the bar by their centers. Since the whole length of the bar is 2 times m plus n, the length of each half is m plus n. The distance of the point of suspension of the right-hand portion of the prism from the point of suspension of the bar is therefore m, and that of the left-hand portion n. The experience that we have here to deal with the weight and not with the form of the bodies is easily made. It is thus manifest that equilibrium will still subsist if any weight of the magnitude 2m be suspended at the distance n on the one side, and any weight of the magnitude 2n be suspended at the distance m on the other. The instinctive elements of our perception of this phenomenon are even more prominently displayed in this form of the deduction than in that of Archimedes. We may discover, moreover, in this beautiful presentation, a remnant of the ponderousness which was particularly characteristic of the investigators of antiquity. How a modern physicist conceived the same problem may be learned from the following presentation of Lagrange. Lagrange says, imagine a horizontal homogeneous prism suspended at its center. Let this prism, figure 7, be conceived divided into two prisms of the lengths 2m and 2n. If now we consider the centers of gravity of these two parts, at which we may imagine weights to act proportional to 2m and 2n, the two centers thus considered will have the distances n and m from the point of support. This concise disposal of the problem is only possible to the practiced mathematical perception. 5. The object that Archimedes and his successors sought to accomplish in the considerations we have here presented consists in the endeavor to reduce the more complicated case of the lever to the simpler and apparently self-evident case, to discern the simpler in the more complicated, or vice versa. In fact, we regard a phenomenon as explained when we discover in it known simpler phenomena, but surprising as the achievement of Archimedes and his successors may at the first glance appear to us, doubts as to the correctness of it, on further reflection, nevertheless spring up. From the mere assumption of the equilibrium of equal weights at equal distances is derived the inverse proportionality of weight and lever arm. How is that possible? If we were unable philosophically and a priori to excogitate the simple fact of the dependence of equilibrium on weight and distance, but were obliged to go for that result to experience, in how much less a degree shall we be able, by speculative methods, to discover the form of this dependence, the proportionality? As a matter of fact, the assumption that the equilibrium disturbing effect of a weight p at the distance L from the axis of rotation is measured by the product PL, the so-called statical moment, is more or less covertly or tacitly introduced by Archimedes and all his successors. For when Archimedes substitutes for a large weight a series of symmetrically arranged pairs of small weights, which weights extend beyond the point of support, he employs in this very act the doctrine of the center of gravity in its more general form, which is itself nothing else than the doctrine of the lever in its more general form. See Appendix Part 3, page 512. Without the assumption above mentioned of the import of the product PL, no one can prove, figure 8, that a bar placed in any way on the fulcrum S is supported with the help of a string attached to its center of gravity and carried over a pulley by a weight equal to its own weight. But this is contained in the deductions of Archimedes, Stevinus, Galileo, and also in that of Lagrange. 6. Huygens indeed reprehends this method and gives a different deduction in which he believes he has avoided the error. If, in the presentation of Lagrange, we imagine the two portions into which the prism is divided turned 90 degrees about two vertical axes, passing through the centers of gravity SS of the prism portions, see figure 9a, and it be shown that under these circumstances equilibrium still continues to subsist, we shall obtain the Huygenian deduction. Abridged and simplified, it is as follows. In a rigid weightless plane, figure 9g, through the point S we draw a straight line, on which we cut off on the one side the length r and on the other the length 2, at A and B respectively. On the extremities, at right angles to this straight line, we place, with the centers as points of contact, the heavy, thin, homogeneous prisms C, D, and E, F of the lengths and weights 4 and 2. Drawing the straight line HSG, where AG is equal to 1/4 of AC and parallel to it the line CF, and translating the prism portion CG by parallel displacement to FH, everything about the axis GH is symmetrical and equilibrium obtains. But equilibrium also obtains for the axis AB, obtains consequently for every axis through S, and therefore also for that at right angles to AB, where the new case of the lever is given. Let us now take a closer look at figure 9 and follow its logic step by step. We begin with a rigid, weightless plane. Think of it as a perfectly flat, massless board. Through a mark point S on this plane, we draw a straight horizontal line. On this line, we measure out two segments. On the left side from S to point A, a distance we call R, and on the right side from S to point B, a distance we call 2. These two lengths are not arbitrary. They represent how far the heavy bodies we will attach are placed from our central point S. At each end, A and B, we place a long, thin, heavy prism so that its center is directly at A or B. The prism on the left, labeled CD, has length and weight marked 4. The prism on the right, labeled EF, has length and weight marked 2. These prisms are rigid and homogeneous, meaning their mass is distributed evenly along their length. Next comes the key construction. From point H on the far end of the left prism to point G near its middle, we draw a slanting line HSG that passes through S. Importantly, the point AG is 1/4 of the full length AC. We then draw a line parallel to HSG that passes through the right prism's end CF. The next step is to take the left prism's portion from C to G and slide it without rotation so that it now occupies the position from F to H on the right side. This is called a parallel displacement. In this new arrangement, everything about the slanting axis GH is symmetrical. Both sides balance perfectly, so equilibrium exists about that axis. Now here's the important deduction. If the arrangement balances about the slanting axis GH, it must also balance about the horizontal axis AB. And if equilibrium exists about AB, it exists for every axis passing through the point S. That includes the axis at right angles to AB, giving us a new, more general case of the lever than before. In short, Huygens uses this geometric shifting of mass to show that the lever's equilibrium can be proved for all orientations through a single central point, not just in the original horizontal setup. Apparently, nothing else is assumed here than that equal weights P and P, figure 10, in the same plane and at equal distances L and L from an axis A prime in this plane, equilibrate one another. If we place ourselves in the plane passing through A prime perpendicularly to LL, say at the point M, and look now towards A and now towards A prime, we shall accord to this proposition the same evidences as to the first Archimedean proposition. The relation of things is, moreover, not altered if we institute with the weights parallel displacements with respect to the axis, as Huygens in fact does. The error first arises in the inference. If equilibrium obtains for two axes of the plane, it also obtains for every other axis passing through the point of intersection of the first two. This inference, if it is not to be regarded as a purely instinctive one, can be drawn only upon the condition that disturbance effects are ascribed to the weights proportional to their distances from the axis. But in this is contained the very kernel of the doctrine of the lever and the center of gravity. Let the heavy points of a plane be referred to a system of rectangular coordinates, figure 11. The coordinates of the center of gravity of a system of masses m prime, m double prime, and so on, having the coordinates x prime and so on, y prime and so on, are, as we know, xi equals the sum over m times x divided by the sum over m, eta equals the sum over m times y divided by the sum over m. If we turn the system through the angle alpha, the new coordinates of the masses will be x1 equals x cosine alpha minus y sine alpha, y1 equals y cosine alpha plus x sine alpha. And consequently, the coordinates of the center of gravity become xi1 equals the sum over m times quantity x cosine alpha minus y sine alpha divided by the sum over m, which equals xi cosine alpha minus eta sine alpha. Similarly, eta1 equals eta cosine alpha plus xi sine alpha. We accordingly obtain the coordinates of the new center of gravity simply by transforming the coordinates of the first center to the new axes. The center of gravity remains therefore the selfsame point. If we select the center of gravity itself as origin, then the sum over m times x equals 0 and the sum over m times y equals 0. On turning the system of axes, this relation continues to subsist. In the direction here indicated, the Archimedean view certainly remained a serviceable one, even after no one longer entertained any doubt of the significance of the product PL, and after opinion on this point had been established historically and by abundant verification. 7. The manner in which the laws of the lever, as handed down to us from Archimedes in their original simple form, were further generalized and treated by modern physicists is very interesting and instructive. Leonardo da Vinci, 1452 to 1519, the famous painter and investigator, appears to have been the first to recognize the importance of the general notion of the so-called statical moments. In the manuscripts he has left us, several passages are found from which this clearly appears. He says, for example, we have a bar AD, figure 13, free to rotate about A, and suspended from the bar a weight P, and suspended from a string which passes over a pulley a second weight, Q. What must be the ratio of the forces that equilibrium may obtain? The lever arm for the weight P is not AD, but the potential lever AB. The lever arm for the weight Q is not AD, but the potential lever AC. The method by which Leonardo arrived at this view is difficult to discover, but it is clear that he recognized the essential circumstances by which the effect of the weight is determined. Considerations similar to those of Leonardo da Vinci are also found in the writings of Guido Ubaldi. We will now endeavor to obtain some idea of the way in which the notion of statical moment, by which, as we know, is understood the product of a force into the perpendicular let fall from the axis of rotation upon the line of direction of the force, could have been arrived at, although the way that really led to this idea is not now fully ascertainable. That equilibrium exists, figure 14, if we lay a cord, subjected at both sides to equal tensions, over a pulley, is perceived without difficulty. We shall always find a plane of symmetry for the apparatus, the plane which stands at right angles to the plane of the cord and bisects the angle made by its two parts. The motion that might be supposed possible cannot in this case be precisely determined or defined by any rule whatsoever. No motion will therefore take place. If we note now further that the material of which the pulley is made is essential only to the extent of determining the form of motion of the points of application of the strings, we shall likewise readily perceive that almost any portion of the pulley be removed without disturbing the equilibrium of the machine. The rigid radii that lead out to the tangential points of the string are alone essential. We see thus that the rigid radii, or the perpendiculars on the linear directions of the strings, play here a part similar to the lever arms in the lever of Archimedes. Let us examine a so-called wheel and axle, figure 15, of wheel radius 2 and axle radius 1, provided respectively with the cord-hung loads 1 and 2, an apparatus which corresponds in every respect to the lever of Archimedes. If now we place about the axle, in any manner we may choose, a second cord which we subject at each side to the tension of a weight 2, the second cord will not disturb the equilibrium. It is plain, however, that we are also permitted to regard the two poles marked in figure 16 as being in equilibrium, by leaving the two others as mutually destructive out of account. But we arrive in so doing, dismissing from consideration all unessential features, at the perception that not only the pulls exerted by the weights, but also the perpendiculars let fall from the axis on the lines of the pulls are conditions determinative of motion. The decisive factors are, then, the products of the weights into these respective perpendiculars let fall from the axis on the directions of the pulls, in other words, the so-called statical moments. 9. What we have so far considered is the development of our knowledge of the principle of the lever. Quite independently of this was developed the knowledge of the principle of the inclined plane. It is not necessary, however, for the comprehension of the machines to search after a new principle beyond that of the lever, for the latter is sufficient by itself. Galileo, for example, explains the inclined plane here in the following manner. We have before us, figure 17, an inclined plane on which rests the weight Q, held in equilibrium by the weight P. Galileo now points out the fact that it is not requisite that Q should lie directly upon the inclined plane, but that the essential point is rather the form or character of the motion of Q. We may, consequently, conceive the weight attached to the bar AC, perpendicular to the inclined plane, and rotatable about C. If then we institute a very slight rotation about the point C, the weight will move in the element of an arc coincident with the inclined plane. That the path assumes a curve on the motion being continued is of no consequence here, since this further movement does not in the case of equilibrium take place, and the movement of the instant alone is decisive. Reverting, however, to the observation before mentioned of Leonardo da Vinci, we readily perceive the validity of the theorem Q times CB equals P times CA, or Q divided by P equals CA divided by CB equals AC divided by CB, and thus reach the law of equilibrium on the inclined plane. Once we have reached the principle of the lever, we may then easily apply that principle to the comprehension of the other machines. The principle of the inclined plane. 1. Stevinus, or Stevin, 1548 to 1620, was the first who investigated the mechanical properties of the inclined plane, and he did so in an eminently original manner. If a weight, as in figure 18, on a horizontal table, we perceive at once, since the pressure is directly perpendicular to the plane of the table, by the principle of symmetry, that equilibrium subsists. On a vertical wall, on the other hand, a weight is not at all obstructed in its motion of descent. The inclined plane, accordingly, will present an intermediate case between these two limiting suppositions. Equilibrium will not exist of itself, as it does on the horizontal support, but will be maintained by a less weight than that necessary to preserve it on the vertical wall. The ascertainment of the statical law that obtains in this case caused the earlier inquirer's considerable difficulty. Stevinus's manner of procedure is in substance as follows. He imagines a triangular prism with horizontally placed edges, a cross-section of which ABC is represented in figure 19. For the sake of illustration, we will say that AB equals 2BC, also that AC is horizontal. Over this prism, Stevinus lays an endless string on which 14 balls of equal weight are strung and tied at equal distances apart. We can advantageously replace this string by an endless uniform chain or cord. The chain will either be in equilibrium or it will not. If we assume the latter to be the case, the chain, since the conditions of the event are not altered by its motion, must, when once actually in motion, continue to move forever. That is, it must present a perpetual motion, which Stevinus deems absurd. Consequently, only the first case is conceivable. The chain remains in equilibrium. The symmetrical portion ADC may, therefore, without disturbing the equilibrium, be removed. The portion AB of the chain consequently balances the portion BC. Hence, on inclined planes of equal heights, equal weights act in the inverse proportion of the lengths of the planes. In the cross-section of the prism in figure 20, let us imagine AC horizontal, BC vertical, and AB equals 2BC. Furthermore, the chain weights Q and P on AB and BC proportional to the lengths. It will follow then that Q divided by P equals AB divided by BC equals 2. The generalization is self-evident. 2. Unquestionably, in the assumption from which Stevinus starts, that the endless chain does not move, there is contained primarily only a purely instinctive cognition. He feels at once, and we with him, that we have never observed anything like a motion of the kind referred to, that a thing of such a character does not exist. This conviction has so much logical cogency that we accept the conclusion drawn from it respecting the law of equilibrium on the inclined plane without the thought of an objection, although the law, if presented as the simple result of experiment, or otherwise put, would appear dubious. We cannot be surprised at this when we reflect that all results of experiment are obscured by adventitious circumstances, such as friction, and that every conjecture as to the conditions which are determinative in a given case is liable to error. That Stevinus ascribes to instinctive knowledge of this sort a higher authority than to simple, manifest, direct observation might excite in us astonishment if we did not ourselves possess the same inclination. The question accordingly forces itself upon us. Whence does this higher authority come? If we remember that scientific demonstration and scientific criticism generally can only have sprung from the consciousness of the individual fallibility of investigators, the explanation is not far to seek. We feel clearly that we ourselves have contributed nothing to the creation of instinctive knowledge, that we have added to it nothing arbitrarily, but that it exists in absolute independence of our participation. Our mistrust of our own subjective interpretation of the facts observed is thus dissipated. Stevinus's deduction is one of the rarest fossil indications that we possess in the primitive history of mechanics, and throws a wonderful light on the process of the formation of science generally, on its rise from instinctive knowledge. We will recall to mind that Archimedes pursued exactly the same tendency as Stevinus, only with much less good fortune. In later times also, instinctive knowledge is very frequently taken as the starting point of investigations. Every experimenter can daily observe in his own person the guidance that instinctive knowledge furnishes him. If he succeeds in abstractly formulating what is contained in it, he will as a rule have made an important advance in science. Stevinus's procedure is no error. If an error were contained in it, we should all share it. Indeed, it is perfectly certain that the union of the strongest instinct with the greatest power of abstract formulation alone constitutes the great natural inquirer. This by no means compels us, however, to create a new mysticism out of the instinctive in science, and to regard this factor as infallible. That it is not infallible, we very easily discover. Even instinctive knowledge of so great logical force as the principle of symmetry employed by Archimedes may lead us astray. Many of my readers will recall to mind, perhaps, the intellectual shock they experienced when they heard for the first time that a magnetic needle lying in the magnetic meridian is deflected in a definite direction away from the meridian by a wire conducting a current being carried along in a parallel direction above it. The instinctive view is just as fallible as the distinctly conscious. Its only value is in provinces with which we are very familiar. Let us rather put to ourselves in preference to pursuing mystical speculations on this subject, the question, how does instinctive knowledge originate and what are its contents? Everything which we observe in nature imprints itself uncomprehended and unanalyzed in our percepts and ideas, which then in their turn mimic the processes of nature in their most general and most striking features. In these accumulated experiences, we possess a treasure store which is ever close at hand, and of which only the smallest portion is embodied in clear, articulate thought. The circumstance that it is far easier to resort to these experiences than it is to nature herself, and that they are, notwithstanding this, free in the sense indicated from all subjectivity, invests them with a high value. It is a peculiar property of instinctive knowledge that it is predominantly of a negative nature. We cannot so well say what must happen as we can what cannot happen, since the latter alone stands in glaring contrast to the obscure mass of experience in us in which single characters are not distinguished. Still, great as the importance of instinctive knowledge may be for discovery, we must not, from our point of view, rest content with the recognition of its authority. We must inquire, on the contrary, under what conditions could the instinctive knowledge in question have originated? We then ordinarily find that the very principle to establish which we had recourse to instinctive knowledge constitutes in its turn the fundamental condition of the origin of that knowledge. And this is quite obvious and natural. Our instinctive knowledge leads us to the principle which explains that knowledge itself, and which is in its turn also corroborated by the existence of that knowledge, which is a separate fact by itself. This we will find on close examination is the state of things in Stevinus's case. The reasoning of Stevinus impresses us as so highly ingenious because the result at which he arrives apparently contains more than the assumption from which he starts. While on the one hand, to avoid contradictions, we are constrained to let the result pass, on the other, an incentive remains which impels us to seek further insight. If Stevinus had distinctly set forth the entire fact in all its aspects, as Galileo subsequently did, his reasoning would no longer strike us as ingenious, but we should have obtained a much more satisfactory and clear insight into the matter. In the endless chain, which does not glide upon the prism, is contained, in fact, everything. We might say the chain does not glide because no sinking of heavy bodies takes place here. This would not be accurate, however, for when the chain moves, many of its links really do descend, while others rise in their place. We must say, therefore, more accurately, the chain does not glide because for every body that could possibly descend, an equally heavy body would have to ascend equally high, or a body of double the weight, half the height, and so on. This fact was familiar to Stevinus, who presented it indeed in his theory of pulleys, but he was plainly too distrustful of himself to lay down the law without additional support, as also valid for the inclined plane. But if such a law did not exist universally, our instinctive knowledge respecting the endless chain could never have originated. With this our minds are completely enlightened. The fact that Stevinus did not go as far as this in his reasoning and rested content with bringing his indirectly discovered ideas into agreement with his instinctive thought need not further disturb us. The service which Stevinus renders himself and his readers consists, therefore, in the contrast and comparison of knowledge that is instinctive with knowledge that is clear, in the bringing the two into connection and accord with one another, and in the supporting the one upon the other. The strengthening of mental view which Stevinus acquired by this procedure we learn from the fact that a picture of the endless chain and the prism graces as vignette with the inscription "Wonder n is geen wonder," the title page of his work Hypomnemata Mathematica, Leyden, 1605. As a fact, every enlightening progress made in science is accompanied with a certain feeling of disillusionment. We discover that that which appeared wonderful to us is no more wonderful than other things which we know instinctively and regard as self-evident. Nay, that the contrary would be much more wonderful, that everywhere the same fact expresses itself. Our puzzle turns out then to be a puzzle no more. It vanishes into nothingness and takes its place among the shadows of history. 4. After he had arrived at the principle of the inclined plane, it was easy for Stevinus to apply that principle to the other machines and to explain by it their action. He makes, for example, the following application. We have, let us suppose, an inclined plane, figure 22, and on it a load Q. We pass a string over the pulley A at the summit and imagine the load Q held in equilibrium by the load P. Stevinus now proceeds by a method similar to that later taken by Galileo. He remarks that it is not necessary that the load Q should lie directly on the inclined plane. Provided only the form of the machine's motion be preserved, the proportion between force and load will in all cases remain the same. We may therefore equally well conceive the load Q to be attached to a properly weighted string passing over a pulley D, which string is normal to the inclined plane. If we carry out this alteration, we shall have a so-called funicular machine. We now perceive that we can ascertain very easily the portion of weight with which the body on the inclined plane tends downwards. We have only to draw a vertical line and to cut off on it a portion AB corresponding to the load Q. Then drawing on a D the perpendicular BC, we have P divided by Q equals AC divided by AB equals AC divided by AD. Therefore, AC represents the tension of the string AD. Nothing prevents us now from making the two strings change functions and from imagining the load Q to lie on the dotted inclined plane EDF. Similarly, here we obtain a D for the tension of the second string. In this manner, accordingly, Stevinus indirectly arrives at a knowledge of the statical relations of the funicular machine and of the so-called parallelogram of forces. At first, of course, only for the particular case of strings or forces, a C and a D at right angles to one another. Subsequently, indeed, Stevinus employs the principle of the composition and resolution of forces in a more general form, yet the method by which he reached the principle is not very clear, or at least is not obvious. He remarks, for example, that if we have three strings AB, AC, AD stretched at any given angles, and the weight P is suspended from the first, the tensions may be determined in the following manner. We produce in figure 23 AB to X and cut off on it a portion AE, drawing from the point E, EF parallel to AD and EG parallel to AC, AB, AC, AD are respectively proportional to AE, AF, AG. With the assistance of this principle of construction, Stevinus solves highly complicated problems. He determines, for instance, the tensions of a system of ramifying strings like that illustrated in figure 24, in doing which, of course, he starts from the given tension of the vertical string. The relations of the tensions of a funicular polygon are likewise ascertained by construction, in the manner indicated in figure 25. We may therefore, by means of the principle of the inclined plane, seek to elucidate the conditions of operation of the other simple machines, in a manner similar to that which we employed in the case of the principle of the lever. The principle of the composition of forces. 1. The principle of the parallelogram of forces at which Stevinus arrived and employed, yet without expressly formulating it, consists, as we know, of the following truth. If a body A, as shown in figure 26, is acted upon by two forces whose directions coincide with the lines AB and AC, and whose magnitudes are proportional to the lengths AB and AC, these two forces produce the same effect as a single force which acts in the direction of the diagonal AD of the parallelogram ABCD and is proportional to that diagonal. For instance, if on the strings AB and AC weights exactly proportional to the lengths AB and AC be supposed to act, a single weight acting on the string AD exactly proportional to the length AD will produce the same effect as the first two. The forces AB and AC are called the components, the force AD the resultant. It is furthermore obvious that, conversely, a single force is replaceable by two or several other forces. 2. We shall now endeavor, in connection with the investigations of Stevinus, to give ourselves some idea of the manner in which the general proposition of the parallelogram of forces might have been arrived at. The relation, discovered by Stevinus, that exists between two mutually perpendicular forces and a third force that equilibrates them, we shall assume as indirectly given. We suppose now, as in figure 27, that there act on three strings OX, OY, OZ, pulls which balance each other. Let us endeavor to determine the nature of these pulls. Each pull holds the two remaining ones in equilibrium. The pull OY we will replace, following Stevinus's principle, by two new rectangular pulls, one in the direction OU, which is the prolongation of OX, and one at right angles thereto in the direction OT. And let us similarly resolve the pull OZ in the directions OU and OW. The sum of the pulls in the direction OU then must balance the pull OX, and the two pulls in the directions OT and OW must mutually destroy each other. Taking the two latter as equal and opposite, and representing them by OM and ON, we determine coincidently with the operation the components OP and OQ parallel to OU, as well as the pulls OR and OS. Now the sum OP plus OQ is equal and opposite to the pull in the direction of OX, and if we draw ST parallel to OY or RT parallel to OZ, either line will cut off the portion OT equal to OP plus OQ, with which result the general principle of the parallelogram of forces is reached. The general case of composition may be deduced in still another way from the special composition of two rectangular forces. Let OA and OB be the two forces acting at O. For OB, substitute a force OC acting parallel to OA and a force OD acting at right angles to OA. There then act for OA and OB the two forces OE equal to OA plus OC and OD, the resultant of which, forces OF, is at the same time the diagonal of the parallelogram OAFB constructed on OA and OB as sides. 3. The principle of the parallelogram of forces, when reached by the method of Stevinus, presents itself as an indirect discovery. It is exhibited as a consequence and as the condition of known facts. We perceive, however, merely that it does exist, not as yet why it exists. That is, we cannot reduce it, as in dynamics, to still simpler propositions. In statics, indeed, the principle was not fully admitted until the time of Varignon, when dynamics, which leads directly to the principle, was already so far advanced that its adoption therefrom presented no difficulties. The principle of the parallelogram of forces was first clearly enunciated by Newton in his Principles of Natural Philosophy. In the same year, Varignon, independently of Newton, also enunciated the principle in a work submitted to the Paris Academy, but not published until after its author's death, and made, by the aid of a geometrical theorem, extended practical application of it. We're going to walk through these geometric theorem referred to as this. If we consider, in figure 29, a parallelogram the sides of which are P and Q and the diagonal is R, and from any point M in the plane of the parallelogram, we draw perpendiculars on these three straight lines, which perpendiculars we will designate as U, V, and W, then P multiplied by U plus Q multiplied by V is equal to R multiplied by W. This is easily proved by drawing straight lines from M to the extremities of the diagonal and of the sides of the parallelograms, and considering the areas of the triangles thus formed, which are equal to the halves of the products specified. If the point M be taken within the parallelogram and perpendiculars then be drawn, the theorem passes into the form P multiplied by U minus Q multiplied by V equals R multiplied by W. Finally, if M be taken on the diagonal and perpendiculars are again drawn, we shall get, since the perpendicular let fall on the diagonal is now 0, P multiplied by U minus Q multiplied by V equals 0, or P multiplied by U equals Q multiplied by V. With the assistance of the observation that forces are proportional to the motions produced by them in equal intervals of time, Varignon easily advances from the composition of motions to the composition of forces. Forces, which acting at a point are represented in magnitude and direction by the sides of a parallelogram, are replaceable by a single force, similarly represented by the diagonal of that parallelogram. If now, in the parallelogram considered, P and Q represent the concurrent forces, the components, and are the force competent to take their place, the resultant, then the products Pu, Qv, and Rw are called the moments of these forces with respect to the point M. If the point M lie in the direction of the resultant, the two moments Pu and Qv are with respect to it equal to each other. 4. With the assistance of this principle, Varignon is now in a position to treat of the simple machines in a much simpler manner than were his predecessors. Let us consider, for example, as in figure 31, a rigid body capable of rotation about an axis passing through O. Perpendicular to the axis, we conceive a plane and select therein 2 points A and B on which two forces P and Q in the plane are supposed to act. We recognize with Varignon that the effect of the forces is not altered if their points of application be displaced along their line of action, since all points in the same direction are rigidly connected with one another, and each one presses and pulls the other. We may, accordingly, suppose P applied at any point in the direction AX and Q at any point in the direction BY, consequently also at their point of intersection M. With the forces as displaced to M, then, we construct a parallelogram and replace the forces by their resultant. We have now to do only with the effect of the latter. If it act only on movable points, equilibrium will not obtain. If, however, the direction of its action pass through the axis, through the point O, which is not movable, no motion can take place and equilibrium will obtain. In the latter case, O is a point on the resultant, and if we drop the perpendiculars U and V from O on the directions of the forces P and Q, we shall have, in conformity with the theorem before mentioned, P multiplied by U equals Q multiplied by V. With this we have deduced the law of the liver from the principle of the parallelogram of forces. Varignon explains in like manner a number of other cases of equilibrium by the equilibration of the resultant force by some obstacle or restraint. On the inclined plane, for example, equilibrium exists if the resultant is found to be at right angles to the plane. In fact, Varignon rests statics in its entirety on a dynamical foundation. To his mind, it is but a special case of dynamics. The more general dynamical case constantly hovers before him, and he restricts himself in his investigations voluntarily to the case of equilibrium. We are confronted here with a dynamical statics, such as was possible only after the researches of Galileo. Incidentally, it may be remarked that from Varignon is derived the majority of the theorems and methods of presentation which make up the statics of modern elementary textbooks.